Welcome to QubitInk. In the previous video, we spent quite a bit of time building the mathematical language behind quantum mechanics. And yes, there was a fair amount of linear algebra. But now we get the payoff. In this video, that mathematics begins to acquire physical meaning. We are going to introduce the postulates of quantum mechanics, the basic rules that connect the mathematical formalism to physical systems. If video 4 was about building the toolbox, this is where we finally start using the tools. So, before introducing those rules, let us quickly remind ourselves what is already in the toolbox. We have vectors and bases, inner products, linear operators, eigenvectors and eigenvalues, and tensor products. None of these ideas was included simply because mathematicians enjoy collecting symbols. Although, admittedly, they do seem quite good at it. Each of these objects is about to take on a very specific role in quantum mechanics. Start with vectors. A vector is an abstract object. Once we choose a basis, however, we can describe that vector using coordinates. The coordinates may change if we choose a different basis, but the underlying vector does not. That distinction between the physical state and the coordinates we use to describe it will become extremely important. Next come operators. An operator takes a vector and transforms it into another vector. You can think of it as a rule, give it a state, apply the transformation, and see where the state goes. Soon, operators will describe some of the most important processes in quantum mechanics, including how closed systems evolve and how measurements act on quantum states. Then we have the inner product. This gives our vector space geometry. It tells us about length, orthogonality, projection, and the overlap between two vectors. And that word, overlap, is worth remembering. Later, these overlaps will become closely connected to the probabilities predicted by quantum mechanics. So the geometry is not decorative. It will become experimentally meaningful. Eigenvectors give us another special structure. When an operator acts on one of its eigenvectors, the direction is preserved. Only a scale factor changes. That simple mathematical property will become central when we discuss observables and measurement. And then there are tensor products. Tensor products tell us how to combine the state spaces of separate systems into one larger state space. One qubit is already interesting. Put several together, and the space grows very quickly. And somewhere inside that larger space, entanglement is waiting for us. We will get there. Now notice what has happened. Vectors, inner products, operators, eigenvectors, and tensor products were introduced as pieces of linear algebra. But they are exactly the pieces quantum mechanics needs. Quantum mechanics is already strange enough. Fortunately, we do not need a completely new kind of arithmetic. What we need is familiar mathematics, together with very specific physical rules. Those rules are the postulates. The postulates provide the connection between the physical world and the mathematical formalism of quantum mechanics. There are 4 fundamental questions we now need to answer. First, what is a quantum state? What mathematical space does it live in? Second, once we have a state, how does it change with time? Third, when we perform a measurement, what outcomes can occur, with what probabilities, and what happens to the state afterward? And fourth, if we have several quantum systems, how do we describe them together? These are the 4 ideas we will study: state space, evolution, measurement, and composite systems. Postulate 1 sets the arena. Postulate 2 gives the dynamics of closed systems. Postulate 3 tells us how information is extracted through measurement. And postulate 4 tells us how individual quantum systems combine into a composite system. So let us begin at the beginning. Suppose we are given an isolated physical system. Before asking how it evolves, before measuring it, and before combining it with anything else, we need to answer a more basic question. What mathematical object represents its physical state? That question defines the arena in which quantum mechanics takes place. And it brings us directly to postulate 1, the state space. So, we have arrived at the first postulate, state space. Before we ask how a quantum system evolves, or what happens when we measure it, we need to know what mathematical object represents its state in the first place. The postulate begins with an isolated physical system. To that system, quantum mechanics associates a complex vector space equipped with an inner product. We call this the state space. For finite-dimensional systems, such as the qubits we use in quantum computing, you can think of this simply as a complex inner product vector space. The phrase Hilbert space may sound rather grand, but the essential idea here is simple: it is the mathematical space in which quantum states live. The physical state of the system is represented by a unit vector in that space. Notice what the postulate is doing. It gives us a general mathematical framework, but it does not say that every physical system must use exactly the same state space. An atom, a photon, and a spin system can require different physical models. The mathematics provides the structure. The physics tells us which state space is appropriate. Now let us make this concrete with the simplest system we care about in quantum computing, one qubit. A single qubit has a two-dimensional complex state space. That means we need two independent basis directions to describe any vector in the space. To describe those vectors, we choose a basis. The standard choice in quantum computing is the computational basis, with the two basis states 0 and 1. In coordinate form, these are simply the two standard coordinate directions. The 0 state points entirely along the first basis direction, while the 1 state points entirely along the second. Nothing mysterious has happened yet. We have simply chosen coordinates for a two-dimensional complex vector space. Once that basis is chosen, every qubit state can be expressed as a linear combination of those two basis vectors. We usually write the coefficients of that combination as alpha and beta. This is the mathematical meaning of superposition. It does not mean that we have abandoned linear algebra. Quite the opposite. Superposition is simply the statement that a vector may contain components along more than one basis direction. Quantum mechanics then tells us how that vector should be interpreted physically. The coefficients alpha and beta are complex numbers, and we call them amplitudes. Because they are complex, each amplitude can contain both magnitude and phase. That phase information may look innocent here, but later it will become essential for understanding quantum interference. At this point, however, we should be careful. We are defining the state space. We have not yet introduced the postulate of measurement. So for now, alpha and beta should simply be understood as the complex coordinates of the state vector in the computational basis. Different choices of these amplitudes give different vectors in the state space. A state can lie close to the 0 basis direction, close to the 1 basis direction, or somewhere between them as a genuine superposition. But there is one more requirement. Not every vector length represents a valid physical state. The state vector must be normalized. Geometrically, this means that the vector has unit length. In the language of inner products, the state has unit norm. And for a qubit written in the computational basis, normalization means that the squared magnitudes of the two amplitudes add to 1. Notice how several pieces from the previous video have now come together. We needed vectors to represent states. We needed a basis to give those vectors coordinates. We needed complex numbers for the amplitudes. And we needed the inner product to define the length of the state vector. That is exactly why the mathematical foundation mattered. So the first postulate gives us a remarkably compact picture. An isolated quantum system is associated with a complex inner product state space. Its physical state is represented by a normalized vector in that space. For one qubit, the space is two-dimensional. We choose the 0 and 1 states as a convenient computational basis, and every qubit state is a superposition of those basis states with complex amplitudes satisfying the normalization condition. That answers our first question, what is a quantum state? But now a new question appears naturally. Once we have a state vector, how does it change with time? And that takes us directly to postulate 2, evolution. We ended postulate 1 with a state vector living in a Hilbert space. Good. Now the obvious question is, once we have that state, how does it change with time? That is the job of postulate 2, evolution. The postulate applies first to a closed quantum system. During the interval we are considering, we treat the system as not interacting with an external environment. Under that condition, the evolution is unitary. Suppose the system is in some state at an initial time, and later we look at it again. Quantum mechanics says there is a unitary operator that maps the earlier state to the later one. The important point is that this operator is determined by the physical evolution between those two times. It is not chosen separately for each possible input state. So if we prepare two different states and subject both to the same closed system evolution, the same unitary operator acts on both of them. The inputs may be different. The rule is the same. That matters because a unitary operator is linear. Once we know how it acts on a basis, linearity tells us how it acts on every superposition built from that basis. Now, why unitary? Remember the geometry we introduced earlier. A valid pure state is a unit vector, and inner products encode the geometry of the state space. A unitary transformation preserves those inner products. As a consequence, it preserves norms and orthogonality. So a normalized state remains normalized as it evolves. The state may move through Hilbert space, sometimes dramatically, but unitary evolution never stretches it into an invalid state. Algebraically, that preservation comes from the defining relation for a unitary operator. Its adjoint multiplied by itself gives the identity. If the evolved state is obtained by applying U to the original state, then its norm is unchanged. U dagger followed by U gives the identity, leaving the original norm. If we started with a normalized state, we finish with a normalized state. There is another structural property worth noticing. Evolution composes in time. Imagine evolving from time 1 to time 2, and then from time 2 to time 3. The total transformation from time 1 to time 3 is obtained by applying those two unitary transformations in sequence. This is exactly the operator composition we already know from linear algebra. Time evolution has inherited the same structure. In quantum computing, this picture is extremely familiar. Quantum gates such as X, Z, and the Hadamard gate are unitary operators. The X gate exchanges the two computational basis states. The Z gate leaves the zero state unchanged and changes the sign of the one state. The Hadamard gate mixes the two basis directions and creates the familiar equal superpositions. So when we draw a quantum circuit and place gates along a wire, we are really specifying a sequence of unitary transformations acting on the state. But the unitary picture also has a continuous time version. For a closed system, the differential law of motion is the Schrödinger equation. The object that generates this continuous evolution is the Hamiltonian. The Hamiltonian is Hermitian. Physically, it encodes the energy structure of the system, and once the Hamiltonian is known, the dynamics are determined in principle. One small notation warning before the alphabet gets us into trouble: here H means the Hamiltonian, not the Hadamard gate. Same letter, very different job. If the Hamiltonian does not depend on time, the Schrödinger equation can be solved using an exponential of the Hamiltonian. That exponential is unitary, so the continuous time picture and the unitary operator picture are completely consistent. This also gives a beautiful interpretation in the energy eigenbasis. Suppose an energy eigenstate has energy E. Under time evolution, that eigenstate keeps the same direction in Hilbert space and acquires a phase factor whose rate is determined by its energy. For a single energy eigenstate, that overall phase does not change observable physics. But for a superposition of different energy eigenstates, the components generally acquire different phases. Those relative phases matter. They change interference, and they are one of the main ways non-trivial quantum dynamics appears. So postulate 2 gives us a very clean picture. Closed system evolution is unitary. The same physical evolution acts linearly on every possible input state. Unitary evolution preserves the inner product geometry of the state space, and therefore preserves normalization. Sequential evolution composes by multiplying unitary operators. For continuous time, the Schrödinger equation describes the motion, with the Hamiltonian as its generator. For a time-independent Hamiltonian, the resulting evolution operator is the exponential of that Hamiltonian. And in the circuit model, the quantum gates we use are precisely controlled unitary transformations. So now we know what a quantum state is, and we know how a closed quantum state evolves. But there is still something missing. A quantum computer is not very useful if we can evolve a state beautifully and then never learn anything from it. Eventually, we have to interact with the system and obtain an outcome. That interaction is no longer the closed evolution we have just described. And that brings us to postulate 3, quantum measurement. Postulate 2 told us how a closed quantum state evolves. The evolution is unitary, deterministic, and completely specified once the physical dynamics are known. But eventually we want to learn something from the system. We have to measure it. And this brings us to postulate 3, quantum measurement. Measurement is different from the closed evolution we have just studied. Instead of describing one deterministic transformation of the state, the measurement postulate gives us a collection of possible outcomes, the probability of each outcome, and the state of the system after a particular outcome has occurred. Let us build that statement carefully. A quantum measurement is described by a collection of measurement operators. We label these operators using an index, usually called m. Each value of m corresponds to one possible outcome of the experiment. So if a measurement can produce several different results, we associate a measurement operator with each of those possible results. The measurement operators act on the same state space in which the quantum state lives. Suppose the system is in some state immediately before the measurement. For every possible outcome m, the corresponding operator acts on that state and produces a vector. It is useful to think of that vector as the branch associated with outcome m. Different measurement operators generally produce different branches. But before the measurement is performed, the postulate does not tell us that one particular branch is guaranteed to occur. Instead, it tells us the probability associated with every allowed outcome. So how do we calculate that probability? Take the branch produced by the measurement operator for outcome m and compute its squared norm. That squared length is the probability of obtaining outcome m. The equation on screen expresses exactly this rule. The measurement operator acts on the incoming state, and the inner product converts the resulting branch into a real, non-negative number. There is another equivalent way to read the same equation. First form the vector obtained by applying the measurement operator to the state. Then calculate the squared length of that vector. A longer branch corresponds to a larger probability. A shorter branch corresponds to a smaller probability. The branch itself, however, is generally not normalized. And that becomes important once an outcome actually occurs. Suppose the experiment produces outcome m. At that point, the state of the system after measurement is determined by the corresponding branch. We take the vector produced by the measurement operator and normalize it. So the post-measurement state is the selected branch divided by its own length. This gives us a valid normalized quantum state again. Notice that postulate 3 therefore gives us two distinct pieces of information. First, it tells us how likely each possible outcome is. Second, once we know which outcome occurred, it tells us the new quantum state conditioned on that result. Those two rules are both part of the general measurement postulate. There is one more condition that the measurement operators must satisfy. If our list of outcomes is complete, then one of those outcomes must occur. The probabilities of all possible outcomes must therefore add to 1. When we substitute the probability rule into that requirement, we obtain the completeness relation. The sum over all outcomes of each measurement operator combined with its adjoint must give the identity operator. This is not an extra piece of decoration. It is exactly the mathematical condition that guarantees that the total probability is 1. In other words, the measurement description has accounted for every possible result. Now let us make all of this concrete with the most familiar example in quantum computing, measuring a single qubit in the computational basis. Suppose the qubit is in a general superposition of the 0 and 1 basis states, with amplitudes alpha and beta. For this measurement there are two possible outcomes, 0 and 1. The measurement operator associated with outcome 0 is the projector onto the 0 basis state. The operator associated with outcome 1 is the projector onto the 1 basis state. These two projectors add to the identity, so together they form a complete computational basis measurement. Notice that this is a particularly simple case. The general measurement operators in postulate 3 do not have to be projectors. Here they are projectors because computational basis measurement is a projective measurement. Now apply the first projector to the qubit state. The component along the 1 direction disappears, leaving only the 0 component. The squared length of that branch is the squared magnitude of alpha. So the probability of obtaining outcome 0 is the squared magnitude of alpha. Likewise, applying the second projector keeps the 1 component and removes the 0 component. Its squared branch length is the squared magnitude of beta. So the probability of outcome 1 is the squared magnitude of beta. And because the original qubit state was normalized, those two probabilities add to 1. This is where the amplitudes we introduced in postulate 1 finally acquire their familiar probabilistic meaning. The amplitudes themselves are complex numbers. The measurement probabilities come from their squared magnitudes. Now consider one actual run of the experiment. Before measurement, the state may contain both basis components. But the measurement produces one outcome. If the observed result is 0, the corresponding branch is selected and normalized, leaving the 0 basis state, apart from an overall phase that has no observable effect. If the observed result is 1, the post-measurement state is similarly the 1 basis state, again up to an irrelevant overall phase. So one measurement run gives one classical outcome, while repeated preparation and measurement reveal the probability distribution predicted by the quantum state. This distinction is important. The quantum state determines the probabilities, but a single measurement produces a particular result. If we want to estimate those probabilities experimentally, we normally prepare the same state many times, perform the same measurement repeatedly, and compare the frequencies of the outcomes. Now we can summarize postulate 3. A measurement is specified by a collection of measurement operators, one for each possible outcome. For a state immediately before measurement, the squared norm of the corresponding measurement branch gives the probability of that outcome. After outcome M occurs, the state becomes the normalized version of that selected branch. And the completeness relation ensures that the probabilities of all possible outcomes add to 1. For a computational basis measurement of 1 qubit, these general rules reduce to the familiar result: 0 occurs with probability given by the squared magnitude of alpha, and 1 occurs with probability given by the squared magnitude of beta. This is a major change from postulate 2. Closed evolution tells us how a quantum state changes without extracting an outcome from it. Measurement connects the quantum state to an observed result and gives a conditional update of the state. For quantum computation, these operational rules are what we will use. There are deeper questions about what measurement ultimately means physically, and those questions are important, but they are separate from the mathematical rules we need here. So far, however, we have still been talking about the state of one quantum system. What happens when our experiment contains 2 qubits, or 2 quantum systems more generally? How do their individual state spaces combine into one description of the whole system? That question leads us to the final postulate. Postulate 4, Composite Quantum Systems. Postulate 3 told us how quantum states connect to observed outcomes. We now have states, evolution, and measurement. One final question remains. What happens when the physical system we care about is built from several quantum systems? This is the job of Postulate 4, Composite Quantum Systems. Suppose we have 2 systems, called A and B. System A has its own state space, and System B has its own state space. When we consider them together, quantum mechanics does not describe the pair by simply placing the 2 spaces side by side. The state space of the composite system is the tensor product of the component state spaces. So the combined Hilbert space is written as the state space of a tensor, the state space of B. This tensor product rule is the mathematical structure that lets quantum mechanics describe several subsystems as one physical system. Let us first look at the simplest case. Suppose system A is prepared in one pure state, and system B is prepared in another pure state. If the joint preparation is a product preparation, then the state of the combined system is the tensor product of those 2 states. For example, if the first qubit is in the 0 basis state and the second qubit is in the 1 basis state, their joint state is 0 tensor 1. We normally write this much more compactly as the 2 qubit basis state 0 1. The first slot refers to the first subsystem. The second slot refers to the second subsystem. This compact notation becomes very useful as the number of qubits grows. Tensor products also determine the dimension of the joint state space. If one state space has dimension dA, and the other has dimension dB, then the composite space has dimension dA times dB. For 2 qubits, each individual state space has dimension 2. The combined state space therefore has dimension 4. Its computational basis consists of 4 states, 0 0, 0 1, 1 0, and 1 1. For n qubits, the same rule gives a state space dimension of 2 to the power n. This exponential growth is one of the central mathematical features of multi-qubit quantum systems. Now we can write the most general pure state of 2 qubits. It is a superposition of all 4 computational basis states, with one complex amplitude for each basis vector. Those 4 amplitudes must satisfy the normalization condition. The sum of their squared magnitudes is 1. At this point, an important distinction appears. Some 2-qubit states can be written as one state of a tensor, one state of B. These are product states. But the tensor product state space contains many states that cannot be written in that form. Those states are entangled. A standard example is the Bell state formed from an equal superposition of 0 0 and 1 1. There is no single pure state of A and single pure state of B whose tensor product gives this Bell state. The state belongs to the joint system as a whole. This is why entanglement is not an extra mathematical rule added on top of composite systems. It appears naturally because the tensor product space is larger than the set of simple product states. The same construction extends to more than 2 systems. For several component systems, the total state space is the tensor product of all the individual state spaces. And when the subsystems are prepared in a product state, their joint state is the tensor product of the individual subsystem states. But again, the full composite space also contains non-product states, including multipartite entangled states. So postulate 4 gives us the framework for describing qubit registers, multi-qubit gates, entanglement, and quantum correlations. Let us summarize the final postulate. The state space of a composite system is the tensor product of the state spaces of its components. Product preparations give product states. Dimensions multiply under tensor products. 2 qubits therefore have a 4-dimensional joint state space, and n qubits have dimension 2 to the power n. The composite space contains both product states and entangled states. And with that, the 4 postulates fit together. And that brings us to the end of video 5. We now have the 4 postulates of quantum mechanics as one working framework. We know what a quantum state is and where it lives. We know how a closed state evolves. We know how measurement connects that state to observable outcomes. And we know how separate quantum systems combine through tensor products. These are not isolated mathematical facts. Together, they form the foundation we will keep using throughout the rest of the series. From here, the focus changes. Instead of introducing the rules, we can start putting them to work in concrete quantum information problems, where multi-qubit states, quantum operations, and entanglement become tools we can actually use. If you are enjoying the series, follow QubitInk for the next lessons. You can also find QubitInk on Instagram, and the contact email is shown on screen. Thanks for learning with QubitInk. See you in the next video.